In the majestic Andes Mountains of South America, engineers split sheer cliffs to build a massive roads, under conditions so extreme that even the smallest mistake can send an entire project sliding straight into ravines, hundreds of meters deep. Yet through millimeter-level calculations, precisely controlled drilling and blasting, and heavy machines weighing hundreds of tons operating while clinging to steep mountain slopes, engineers have managed to create winding roads that trace the mountainsides like steel threads, reconnecting regions that were isolated for centuries. Are you curious how engineers can force a road to cling to near vertical cliffs? Join Quantivox Tech as we explore what comes next. Overview of mountain roads. In the Andes, building roads is not just a transportation challenge. It is a direct confrontation with some of the harshest terrain on the planet. Many highways in Peru, Chile, and Bolivia are constructed at elevations of 3,000 to 4,500 meters, where thin air can reduce labor efficiency by 30 to 40%, and weather conditions can shift from intense sunlight to snowfall within just a few hours. In these projects, more than 6% of the total cost is not spent on the road surface itself, but on rock excavation, slope stabilization, and landslide prevention. In response, mountain roads in the Andes are usually built into main stages. The first stage follows the outer cliff face, where engineers cut the road directly into the mountain, stabilize the slope with anchors and retaining structures, and protect the roadway from rock falls. When the terrain becomes too steep or unstable, construction shifts to the second stage, tunneling through the mountain, allowing the road to bypass the most dangerous sections while reducing exposure to landslides and extreme weather. Construction process on cliffs. And now we will take a closer look at each stage of building a road along the cliff, starting from the moment the mountainside is still completely untouched. The first step in the process is to precisely determine the road centerline and mark the construction boundaries directly on the rock face. Based on this layout, drill holes are ranged according to pre-calculated plans, and explosives are carefully loaded in controlled amounts to break the rock in sections, ensuring that the overall stability of the mountain is not compromised. After each blast, once the rock has been loosened, excavators move in to pick up and remove the fragmented soil and stone, gradually clearing the construction surface. The material is then loaded directly onto heavy-duty trucks positioned along the edge of the road, ready for transport out of the site. These trucks operate continuously along temporary access roads, hauling debris to designated disposal areas planned in advance. In certain sections where the terrain allows, bulldozers may push the material directly down into the river or steep slopes below, shortening the time required for site clearance. Next, bulldozers take on the role of shaping the road, pushing away excess material and gradually carving the mountainside into the initial roadbed form. The blade is constantly adjusted to achieve the required slope and an elevation, creating a rough but stable surface for further operations. This cycle of drilling, blasting, excavating, bulldozing, and grading is repeated section by section, until a continuous roadway gradually takes shape, firmly anchored to the steep and dangerous cliff face. Once the ground surface has been leveled and stabilized, graded aggregate or crushed stone is delivered by trucks and dumped in strips along the road alignment. Wheel loaders then move in to scoop and redistribute the material evenly, preparing it for the next construction layer. After that, motor graders run along the route, spreading the material into uniform windrows and adjusting the elevation precisely, according to the longitudinal and cross-sectional design profiles. When the road shape meets the required specifications, water trucks spray the entire surface to control dust and create suitable moisture conditions. For compaction, vibratory rollers or steel-wheeled rollers then begin compacting each layer, moving in multiple overlapping passes to achieve the specified density. In curved sections or areas close to the cliff face, graders continue to fine-tune the road edges and cross-slope to ensure proper drainage. Next, rollers move along the route in multiple overlapping passes, compacting each layer of material to create a firm, stable, and uniform roadbed before the surface layer is constructed. In narrow sections close to the rock face or in areas where rollers cannot access, workers use hand-operated compactors to densify each layer of material, ensuring uniform compaction and preventing localized settlement of the roadbed. After that, workers secure themselves with safety harnesses and carefully climb the steep cliff face to access the rock surface directly. There they use pneumatic drills to bore into uneven sections, breaking off protruding rock blocks to flatten and stabilize the slope. This work is carried out point by point, with continuous checks on the surrounding rock cohesion to prevent sudden rock falls or slope failure. Throughout the operation, all workers wear full personal protective equipment including helmets, safety harnesses, masks, and gloves to minimize risks while working in extremely hazardous terrain. Afterward, the entire cliff face is covered with a protective steel mesh, which helps secure loose rock fragments and reduces the risk of rock falls onto the roadway below. Next comes the asphalt paving stage. Before laying the main asphalt layer, workers spray a thin coat of liquid asphalt onto the roadbed to create proper bonding between the structural layers. This asphalt coat is then heated using gas burners, allowing the solvent to evaporate and activating the asphalt's bonding properties. During the asphalt laying stage, the paver moves slowly along the road, continuously receiving hot asphalt mix from dump trucks feeding directly into the front hopper. Behind the machine, the heated screed keeps the asphalt in a workable state, while spreading it into a smooth continuous surface. Workers stand on both sides of the paver, closely monitoring the edges and using shovels and hand rakes to correct uneven areas or sections close to the road shoulder. Heat and smoke rising from the pavement indicate that the asphalt remains at a very high temperature, requiring the entire crew to work in close coordination and with precise timing. Some workers follow directly behind the paver to treat joints, gaps, or curved sections, where the machine cannot maintain full control. The pace of both the paver and the supply trucks must remain steady to avoid interruptions. In the pavement layer, as the machine advances, a continuous strip of black freshly laid asphalt gradually takes shape, marking the most visible stage in completing the mountain road. After the asphalt layer has been laid, workers use high-pressure sprayers to clean the surface and remove any remaining loose stones or excess material. The spray nozzles are moved evenly to ensure the roadway is clear and that the asphalt's bonding and surface quality are not affected. Once the asphalt section is completed, the road surface gradually cools and becomes a solid continuous layer, clearly revealing the curves that closely follow the mountainside. From above, the winding road resembles a black ribbon draped across the cliff face, marking the completion of an engineering work built in extremely harsh terrain. Construction process of mountain roads using precast concrete. In areas where the cliff face is almost vertical and there is no longer enough space to cut or widen the ground, the road must be suspended along the mountainside using a system of reinforced concrete columns and prefabricated modular sections. Instead of excavating deeper into the mountain, engineers shift to a vertical construction approach using the space below as load-bearing foundations. First, large concrete columns are built directly onto the bedrock, acting as the primary structural skeleton that supports the entire roadway above. Due to the extreme terrain, most materials cannot be delivered by conventional vehicles and instead must be placed using cranes, specialized transport equipment, or lowered from above into their exact design positions. Once the columns are completed and have reached the required strength, the road deck modules are installed section by section, much like assembling giant Lego blocks on the mountainside. Each module is prefabricated to standard dimensions and includes steel girders, concrete slabs, and connection points, significantly reducing on-site construction time. Workers operating at height must always be secured with safety harnesses and work in close coordination with crane operators to precisely align each component. As the modules are locked onto the columns, the structure gradually forms a continuous roadway that follows the contours of the mountain. Finally, the road surface is finished and safety barriers and drainage systems are installed to ensure long-term safety and durability. This approach not only allows roads to cross cliffs that would otherwise be impossible to build on, but also significantly reduces the amount of rock excavation required. It represents a combination of modern structural engineering and an adaptive build with the terrain mindset, enabling transportation infrastructure to exist sustainably even in the harshest mountain environments. Tunnel construction through the mountain. And as mentioned at the beginning, when neither carving the road into the cliff face nor building it on supporting columns is feasible, the next solution is to route the road directly through the mountain by constructing a tunnel system. The project is given its first breath. The ventilation system at depths of hundreds of meters where pressure, dust, and heat can make the air toxic within minutes. Engineers must create an artificial network to sustain life underground. From the construction center, vertical shafts are drilled up to the surface, each about 4 to 6 meters wide and up to 200 meters high, bringing in fresh air while expelling exhaust gases. Inside, sensors constantly monitor oxygen levels, temperature, and toxic gases, coordinating powerful jet fans to keep airflow steady. These ventilation shafts are built using the raised boring technique, where the drill head is operated from inside the tunnel and pushed upward toward the surface, with near-perfect precision. Once completed, the entire network becomes the lungs of the project, allowing hundreds of workers to labor for hours beneath the mountain, while still breathing the air of life. Outside, the construction site is shrouded in a haze of dust, while deep inside the mountain, a colossal machine is slowly being assembled. The tunnel boring machine, a true symbol of the modern infrastructure era. Positioning this giant for its first operation is a highly complex process that demands absolute precision and seamless coordination among hundreds of engineers. The entire system is delivered to the site through hundreds of specialized transport vehicles, each carrying modules weighing from dozens to hundreds of tons. From the supporting frame and control cabin to the hydraulic systems and the cutter head, the heaviest component weighing over 1/500 tons and nearly 15 meters in diameter. Auxiliary tunnels are widened and temporarily reinforced with steel and sprayed concrete to make room for these massive components. In the confined space illuminated by hundreds of industrial lamps, the modules are connected and aligned using laser sensors with a tolerance margin of no more than 5 millimeters. Powerful hydraulic jacks lift the cutter head into position, linking it step by step with the body and tail sections according to a predetermined sequence. Once fully assembled, the entire tunnel boring machine stretches nearly 100 meters long, the equivalent of a 30-story building laid on its side, with thousands of mechanical parts perfectly fitted together, forming a unified steel giant ready to pierce through the solid heart of the mountain. From the central control cabin, the electrical, hydraulic, and pneumatic systems come alive. In an instant, the mountain trembles slightly. The tunnel boring machine begins to move, nearly 100 meters long and weighing over 3,000 tons. The machine advances slowly yet powerfully with thousands of mechanical components, working in perfect harmony. At this stage, the cutter head is already buried deep in the rock, while the rear section is still being assembled in the launch chamber, a process requiring precise coordination between power, water, air, and conveyor systems that must run without interruption. At the front, four massive hydraulic cylinders press the cutter head against the rock, with up to 500 tons of force. 23 alloy discs spin with immense torque, crushing layers of rock as hard as steel. Each drilling cycle advances about 1.2 meters, taking roughly 30 minutes and repeating more than 50 times per shift. The crushed rock is collected and carried out by an automated conveyor, while high-pressure water jets constantly cool and clean the cutter head, reducing friction. Once a cycle ends, the gripper shield pushes forward. Hydraulic clamps lock onto the tunnel walls and the next cycle begins. This rhythm press-release advanced drill repeats endlessly day and night until the tunnel is complete. In monumental projects like Europe's Santa Lucia Tunnel with a TBM diameter of nearly 16 meters, or Switzerland's 57-kilometer Gotthard Base Tunnel, the machines operate 24 hours a day with unmatched precision. Yet today, China leads this underground frontier, with over 1,000 TBM simultaneously carving railways, subways, and hydroelectric tunnels, a true symbol of its determination to conquer the depths with technology. Which nation's tunneling innovation impresses you the most? Deep inside the mountain, the drilling has stopped, but the work is far from over. Engineers, now carrying measuring instruments instead of drills, quietly enter the tunnel, where every meter of concrete must prove its strength. Pressure sensors and ground-penetrating radar scan the walls, detecting cracks thinner than a hair. High-frequency ultrasound and 8K optical cameras inspect every bolt and seal to ensure flawless safety. In the control room, hundreds of real-time indicators track the tunnel's lungs. Jet fans, smoke sensors, drainage pumps, and a 10-megawatt backup power system, all tested under strict NFPA 502 and EN 505 I4.5 standards. Every reading and vibration is recorded and analyzed until perfection is reached. Only then is the tunnel declared ready. A true symbol of precision and human resilience beneath the earth. Conclusion. So you've just joined us in exploring the entire process of building roads on cliffs. From clinging to the rock face and erecting concrete pillars to sections that require traversing the heart of the mountain. The information in this video has been compiled and filtered from various sources. If you have any further questions, please feel free to leave a comment below. And now goodbye and see you in the next videos.